Hi again, everybody. Welcome back. So we've started talking about optics, which is the study of these oscillating electromagnetic waves that we've been talking about. And they're more commonly known as light. And we're going to slowly start shifting over to referring to it as light because, well, that's what everybody does. But don't lose sight of the fact that it is an oscillating electromagnetic wave. And so everything we've learned about electricity and magnetism applies to these waves that we're talking about here. We're going to start looking at some of the effects of when I start combining these waves. We talked about this a little bit last time. We talked about how when I had these spherical wave emitters, these wavelets moving out, where those wavelets interfered with each other, we would get the next wavefront. And so this allowed us to plot how a wavefront would be traveling. And we saw that this is what makes light bend around corners or sound bend around corners and water waves and a whole bunch of other things, pretty much any kind of wave. So what we're going to talk about now is, suppose I have two light rays, two independent ones. So not just the wavefront emitting and getting to the next one, but I'm going to have two independent wavefronts coming together. What happens when they come together? Well, as you might expect, when they're in phase, they're going to interfere constructively, and it's going to be bright. Where they're out of phase, where they're 180 degrees out of phase, when this electric field is positive and this electric field is negative, then they're going to cancel each other out because the electric field is a vector. So let's see what we can do mathematically now to see what kind of pattern we'll get when these two different kinds of electromagnetic waves combine. Let's get started. All right, so take a look in your book under interference. This is microtask 1. And we want to start to get an idea of what pattern is going to be produced. So now we have not just one slit, one aperture, but two. And so let's see what kind of pattern that we can get with this. Let me switch to my pen. So what we want you to do, each of these dashed lines that you see here, let's use a different color. Each of these dashed lines that you see here, I've drawn that to represent where I will get the two spherical waves are going to be in phase. Now, let's make sure that we're all understanding what we mean by that. So this wavefront, this top wavefront, is being produced by this aperture right here. And then I have another one that's extending out here. But notice that it extends out in all directions. So if I have one, the one on the bottom is looking like this. And then we use a different color here. The one on the top is looking like this. And this is very similar to what we did when we were talking about the wavelets that were on the line here, except now they're being produced by two separate apertures from this. So wherever these two combine constructively, they're in phase, and so it's going to be bright. If they combine destructively, 180 degrees out of phase, then they're going to be dark. So what we've done with the dashed lines that you see here is everywhere that you see a dashed line, that's where I'm indicating, okay, right here along this path is where they happen to be in phase from that. So at this point, for example, right here, then both the top wave and the bottom wave, the lines have actually intersected with each other. And the lines that are representing the peaks have intersected with each other. And so that's going to indicate where we've got constructive interference. Okay, now that you've got that, you should be able to very easily label where am I going to get bright and where am I going to get dark. So go ahead and do that right quick. Well, remember, constructive interference, if they're in phase, is going to give me a bright spot. So I've got a bright spot here, I've got a bright spot in the middle, and a bright spot down here. The one in the middle is maybe the easiest to see. You can see that that's where those lines are intersecting right there as we look at it here. And you may say, well, okay, well, what about the part in between? Well, if it's not bright, it's going to be dark. So we'll label those with dark. And that's going to be something that we're going to be using quite a bit here. Sometimes we can't actually plot the position of the dark fringes. That's what these little lines are going to be called. We can't plot the position of those destructive interference points. Instead, we know that they occur halfway in between the places where I have the bright constructive interference, where they're actually directly in phase. All right, so now if we're going to color in what that looks like, and I'm going to do this kind of off, let's do it in red. So let's say I had a red laser then I'll get that central bright point in the middle. And then we would have this one over here, and maybe they're going to be fairly big. And then I would have this over here. Now I also have interference extending out this way and this way. Because if you think about it, those waves are still expanding out. And so even further on out, I'm going to get places where I have this constructive interference. So this pattern, this bright and dark oscillating pattern, extends outward all the way out through here. Now, most of the energy, as we talked about last time, is going to be going through the center. That makes sense, right? So most of the energy is going to be going through the center, so it's going to be the brightest. Conservation of energy, I've got a limited amount of energy. The total energy on all of those little bright spots has to equal the total energy in the two lasers from here. So that would mean that the amount of energy in each one of these bright spots as we move out has to get less and less and less. Okay. So this pattern that you see here is called an interference pattern, because they're interfering with each other. And by tradition, we call the lines themselves, the bright spots, are called fringes. And you can think about that as, because you've got fringes on a curtain or some sort of cloth dangling down like that. It's kind of what it looks like. We talk each band we call a fringe order. So this central one is the 0th order fringe. It's the central maximum. This is a first order fringe. This is also a first order fringe because it's the first one on either side, and they will have the same brightness. They will have the same intensity. If I have another one over here then, which may be off my screen, that would be the second order and third order, and so on and so on and so on. And traditionally what we'll use is an integer to indicate that. So we would say that this would be the m equals 0 fringe, this would be the m equals 1, m equals 2, and then I might say that this is m equals minus 1, m equals minus 2 if I want to indicate which side I'm on. Realistically, you're going to get the same. It's the same distance, just doesn't matter which way you're going. Okay, so this key right here, this is our interference pattern. And it's very simple to think about. It's simply where my two waves are interfering. Do want to make one comment though. Take a look over here. I've been talking about having two lasers. I don't actually have two lasers in this particular case, do I? I have a single laser that's firing upon these two slits. But remember, because each one of these slits has its own wave emitters as it comes through, it acts like I have two lasers there. I could do the exact same thing if I had two physical lasers shining and interfering with each other. The problem that I have is I've got to get these things lined up to be exactly aligned with each other. They also have to have exactly the same wavelength for everything that we're talking about here. And there's always going to be some variation in what we're looking at. So usually if I want to get this kind of pattern, I want to have a single light source that's passing through two apertures, through two slits. And then I'll get these kind of patterns that we're looking at. Okay. All right, let's move on to the next one. We'll get rid of this. Maybe we'll get rid of this. There we go. Okay. So I've zoomed in on our pattern here that we've been looking at. So this is what we had before. And here, this line that I'm drawing, I'm going to use that to represent the direction these wave fronts are propagating. So this is perpendicular to my wave fronts. So this would be the same picture that I had before, but instead of having my wave fronts moving this way, I'm just going to say, okay, I'm tired of drawing all those curved lines. So I'm going to draw that path perpendicular to them. Okay. So that path right there is perpendicular to these wave fronts, but it shows the direction in which the wave fronts are moving. This, by the way, is the origin of the light ray that maybe you've heard about before. But really, it's nothing more than a notational convenience. It just, because I'm lazy, I don't want to draw all these lines that are here. So instead, we'll say, okay, this path that you see right here, then, that's the path of all of those waves moving this way. Whereas this one is going to be the path of all of these waves. Get my mouse to release there. There we go. All right. So let's get rid of this. So furthermore, we've zoomed in on this area right here so that you can see a little bit better what's going on, because we're going to need to use some geometry to figure out what's happening here. So D is the distance between the slits, between the apertures. All right. Now, these two waves are the waves that are being emitted from the, we'll call it the center here. Again, though, remember that I've got multiple wavefronts coming out here, but this is one wave and this is the other wave. So we look at microtext 2 then. If the path length difference is exactly one wavelength, what type of fringe will appear where they interfere? And we did this last time. Let's go ahead and draw that. Suppose we'll draw this down here to the side. We talked about how if I have two electromagnetic waves, so here's my E field, but I'm going to have one that's going to start out back here. So it's going to travel a slightly longer path to reach this. So this will be E2 and this will be E1. And that's the best I can do with that. So you see that if I am exactly one wavelength away, so if my path length is exactly one wavelength longer, then they will be in phase. So if they're exactly one wavelength, then I'm going to get a bright fringe. If they're half a wavelength, then by the time they meet together, then they're going to be out of phase, and they're going to cancel each other out. Okay, so we want to come up with a mathematical expression for the difference in the path lengths. Now, here's the hint that we give you. This length, let me do this in red so that we can see it. This length and this length are the same. And this ray goes all the way to my screen. Okay. So you may say, oh, well, wait a minute, how can these two ever be the same if they're parallel to each other? Well, remember the small angle approximation. If that angle is very, very small, and it's a long way away, then I can consider them to be parallel way back here from this. But the key thing we want to recognize is that everything to the right of the dashed line that you see here, that dashed line right there, that's all the same length. So what can you say about X? X is this distance here, and it goes from here to here. If I have a bright fringe, what can I say about X? Well, X must be equal to one wavelength, right? So X must equal lambda in order to get a bright fringe. That's the key condition. In order to get a bright fringe, then I'm going to have X equal to my lambda there. All right, so now we can use trigonometry then. I'll get a bright fringe whenever X is equal to lambda. So X, though, is going to equal, let's say that I think we defined this to be, yeah, you can barely see it right there, but this is my angle theta right here. If I blow this up even more, that's theta, okay? So how would I write that in terms of trigonometry? Well, X is going to be the opposite. Notice that D, lowercase d here, this is the hypotenuse of my triangle. Let's draw that and make sure that everybody sees that. That's the hypotenuse of my triangle. That's X. This is theta. So is that going to be sine, cosine, or tangent? It's going to be a sine. So this is going to be, let's go ahead and write it out from full first. The sine of theta is going to be the opposite over the hypotenuse, so X over D. And so that means X is going to equal to D sine theta. Now that's true for anything, right? X, it doesn't matter whether I'm one wavelength in phase or not. However, if I am actually going to have bright fringes, I need that distance X to equal one wavelength. So let's scroll up here. So we want to find the mth bright fringe. And by that we mean, remember, our zero order fringe is going to be in the middle, then our first order, second order, third order. And each one of those times I have to have a distance equal to a multiple of the wavelength. Let's do it for the first fringe to start off with. Well, that one we said, okay, I have x equals d sine theta, but for the first fringe, that's equal to exactly one wavelength. And so that's going to be m is equal to d sine theta. So that gives me the location of the first m lambda, sorry. If m equals 1, that gives me the location of the first fringe. If m equals 2, now they're 2 lambda apart. They're 2 wavelengths apart. They're still going to be in phase, though. Make sure that that makes sense to you. If they're 1 wavelength apart, let me draw our picture again. So here's one of our waves. That's kind of our comparison line. If I'm 2 wavelengths out, 1, 2. You see that I'm still going to get constructive interference. So I'm still going to get bright fringes where they interfere with each other. So this then is my general, where it's plus or minus 1, plus or minus 2, plus or minus 3, and so on and so on. Okay. Now, what about the dark fringes? Well, the dark fringes occur when it's half a wavelength. So the way that I can think about that then is it's going to be m plus a half times lambda is going to equal d sine theta. And of course, if m is 0 up here, that's going to be my central bright fringe. If m is 0 here, well, then that's going to be I'm half a wavelength out. And so now they're going to destructively interfere. Let's make sure that we can see that. So here's E. There's my comparison wavelength. Here's my line here. And that would be a whole wavelength, but if I stop right here, let's go ahead and sketch it now that we have our distance. You see that now they are going to be out of phase. They're going to be 180 degrees out of phase. Okay, so you see that when we put all of these patterns together, we're going to get something that kind of looks like what we see here. The central bright fringe, and we're showing this here on this way. So this would be our central bright fringe. And then the fringes get dimmer and dimmer and dimmer as we move outward in either direction. Now, on the right here, we've got another graph that we're going to find very useful through here. This is showing the intensity. And yeah, in this case, it's going to be the intensity. It's not going to be the current or the moment of inertia and everything else we've got. But versus some distance, and maybe we'll call that x. So this peak then is showing us that this fringe is bright because it's got the highest intensity. So this would be our m equals 0, our central fringe, or central maximum. This then might be m equals minus 1, m equals minus 2, m equals minus 3, and so on. And then, of course, on the other side, we've got m equals 1, m equals 2, and m equals 3. And that extends on to infinity. And like I said, it actually does extend on infinity. I mean, this theoretically extends all the way to the moon, but because of conservation of energy, there's very, very, very little light, very little energy by the time I get out very many orders away from that. And so it's beyond anything that you would ever hope to detect, and it's going to get lost in any kind of background information that we have. Okay, so now here's a little puzzle for you. Suppose I don't just have 2 fringes, but suppose I have more than 2. So for example, if I have 3 fringes, how is our expression going to change? So we want to come up with a mathematical expression for that. And the way to do that, the way to approach it is, okay, I want to come up with an expression that holds if I have 2 fringes, because we already know what that looks like. And we're just going to sketch that out to the side here. But remember, that's going to be m plus 1/2 lambda is d sine theta, right? Because then when m is 0, I'll get half a wavelength. When m is 1, I'll get 3/2 of a wavelength, and so on and so on and so on. So whatever we get when we have n slits needs to also satisfy that when n equals 2. So pause the video and think about it. Just a little bit of a challenge, a little bit of a puzzle. See if you can figure it out. Challenge yourself. Okay, so one possibility might be to say, and I'm going to use k instead of m just so that we don't get confused between which is which. If I have k over n lambda equals d sine theta. That kind of works if we think about it. So if I have k equals, well, if k equals 0, that doesn't work, does it? Because that's going to give us a bright fringe, right? So let's start with k equals 1. And again, we're going to test it for n equals 2. If k equals 1, then I get 1/2 lambda. That works. But if k equals 2, that doesn't work, does it? How about 3? Okay, that works. 4, because 3 then would be 3 divided by 2, 3/2. And 4 is not going to work, but then 5 is going to work, and so on and so on. And you say, okay, well, cool, I'll just do all of the odd numbers until we start to decide, okay, well, what if I have 4 fringes? What if I have 3 fringes? So if n equals 4, right, then I should get it at 1/2, at 1/4, 1/2, and 3/2. Well, okay, 0 obviously still is not going to work. 1 works. 2 now, the 2 is actually 2/4 is going to be 1/2. That's going to be a dark fringe. That's what we want. 3 still works. That's 3/4. 4, though, does not work. Do you see that? Because now I've got 4/4, and that should be a bright fringe. And hopefully you can see the pattern. What this is going to happen is that, yes, this works, but if this assumes that k/n is not a whole number. So that would be our formal solution to the puzzle, would be this is going to be the equation for the dark fringes, and it's going to be k as an integer, 1, 2, 3, 4, 5, and of course negative signs too, but 1, 2, 3, 4, 5, but with the exception that k/n is not a whole number, and that'll apply to everything. Now, some students get a little bit confused because my bright fringes, of course, are going to be in the same spot. So what you see here, all of my bright fringes have to be exactly where they were before. But now I'm saying I've got dark fringes in between. Well, how do you have a dark fringe without also having a light fringe? And in fact, we do. They're called secondary maxima. They're much, much fainter than the primary. And so what happens then is, let's say that this was my original. Well, let's say that my original was quite wide, like you see here on this side. Then what happens is, since I'm getting more dark fringes and then some very, very faint light fringes in between, then the end result is that my bright fringes actually get narrower, my primary bright fringes. These still look mostly dark, but if you look very carefully, you can see that it gets a little bit brighter here, then dark, then a little bit brighter here, then a lot brighter, and then so on and so on. So what is happening then to the energy? Remember, it's conservation of energy. I've got less energy being spread out over this big distance here. Well, the energy is going to be the same, but it's over a smaller area, which means the intensity is going to go up. Because remember, intensity is going to be our power, the amount of energy per time, divided by that area from that. So that means, you can think of it this way, I'm taking the same amount of light and I'm concentrating it in a smaller area. And so these things are going to get brighter as a result. And the more fringes, the more slits I have, the more apertures I have, the thinner these lines are going to be, and therefore the brighter they're going to be. You have probably seen, you probably called them rainbow glasses, but you put them on, you see rainbows everywhere from those. Those are actually something called a diffraction grating. And a diffraction grating is often a piece of glass or plastic in which we've engraved slits in them. We don't actually have to cut a hole all the way through it, because the flat plane, remember, is not going to diffract anything. It's just going to let everything go straight on through. But I will put thousands of lines right next to each other, thousands of tiny little slits. So in the space of, where here we might have had one slit, if I've got my 2 slits this far apart, now I've got 1,000 slits in that same amount of space. That means that the diffraction lines, these interference fringes that you're going to get, are going to be very, very thin. And then they'll, of course, be very, very bright. So a diffraction grating is one of the better ways that you can see this interference pattern. It's actually easier than even just taking, okay, I've got 2 pieces of cardboard, I'm going to put them next to each other. Yeah, you'll get fringes from that. You absolutely will. but they're going to be very wide. They're not going to be terribly bright, and it's going to be hard to see. By using one of these diffraction gratings, then we can get it a nice, sharp, and bright diffraction pattern that we can see. Now, if we look down here, and there's a discussion here, that's what we're talking about with diffraction gratings. You may say, well, why do we see rainbows instead of individual bright images? So if my light, is shining through it, white light, for example, why am I getting rainbows? Well, remember that white has all of the different colors in it. So this is going to be important for us, but white has all the different colors of the rainbow in it. So for the visible wavelength, that's anywhere from 400 nanometers to 650 nanometers or so. But each one of those has a different wavelength. Each color has a different wavelength. And so if we go back to our expression for our bright fringes, because that's what we're mostly interested in looking at, it's going to depend upon the wavelength. So that means that the angle is going to be different for each of the different colors. So let's solve for the angle here. I get m lambda over d is going to equal sine theta. So you see that as lambda gets smaller, which corresponds to blue light, we're going to learn, then sine theta also has to get smaller. And that tells me that that angle there has to change as well. So what happens then is that since the angle is changing, blue and red will be in different positions. And so that white light is getting split, and that's what's causing your rainbow. All right, so let's see if we can do a problem with this then. Go ahead and delete this part, and then we'll erase what we've got here on the sides. And this is very similar to what maybe you would do in a lab experiment. The way a CD works, a CD-ROM, CD, audio CD, anything like that, is it burns. So I've got basically a reflection. I've got a reflective surface here, a mirror, say, and then on top, I've got some plastic that I'm burning these grooves into. And those bits, those bumps, that's what encodes the data so that you can see that. Well, those things are very, very, very close together. Now, remember that if I have a light ray coming in, if it hits the mirror part, it's not going to be affected. It's just going to come straight back. But it can't make it through these grooves. So this acts like a diffraction grating. So this effectively then becomes a slit. And in fact, it's multiple slits, which is why we're going to get a nice tight diffraction pattern. If you've ever looked at a CD or a DVD, you can often see that rainbow reflected in there. That's because the light's being diffracted different amounts. So the different colors are being sent off at different angles, and so that you're able to split that. Well, we can use this property to figure out what is the spacing between this. We can literally measure things on the order of a micron, but 1/1,000,000th of a meter using this technique. Interference is a very powerful technique for doing this. Okay, so let's take an example. So let's say that we've got a red laser pointer, and it's about 650 nanometers-ish. It's not exactly that, but you'll find it printed on the laser. And we're going to reflect those fringes onto a screen that's 40 centimeters away. So this, we'll call this capital D, and we're going to say that that's going to be 40 centimeters away, or 0.40 meters. Okay, we measure the distance between the central, here's our central, this is m equals 0, and this is m equals 1. So this is our first bright point here. Here's our central one, here's a bright one. We measure that distance, and we'll call that A, to be 16 centimeters apart, so 0.16 meters. All right, we want to know what is this D, the spacing in between those bumps, those grooves that are making the diffraction pattern that we see. All right. This would be a really worthwhile exercise for you to pause the video and see if you can work it out in your book, because it's basically, you've got everything that you know. It's going to be exactly the same kind of thing that we've done. Go back and look through the earlier part of this section, and it'll give you the zoom in part on the geometry of what's going here, and you'll be able to figure it out. So pause the video, see if you can get it, and then we'll come back and we'll work through the problem. Okay, You got it? Let's see how you did. So for our design, we're going to assume that the spacing on the CD, so that's between those bumps, those grooves on the CD, is going to equal D. That's going to be our slit width. We're also going to assume that D is much less than big D, so that I can use this small angle approximation. And that's pretty reasonable, considering these are going to be the order of a micron, right? And then we're going to use our diffraction expression to get D. All right, so let's define our quantities. So D is going to be our distance, and so that's going to be 0.40 meters. Let's be really clear, that's the distance to the screen, because we've got a number of different distances going on here. We defined A, 0.16 meters, and that's going to be the distance to the M equals 1 bright fringe. And I'm setting this to be my 0 for distance, and there's no reason not to, right? I can set my M equals 0. I can set my 0 anywhere I want, so I'm going to set the location of my bright fringe, my central bright fringe here, to be 0. So A is now that distance through here. Okay. All right, let me zoom up a little bit so that we can see what's going on. There we go. Okay, and we want to find D in meters, and that's going to be the distance between the grooves, which is also the slit width. And then the last thing we know is that our wavelength is going to be 640 nanometers, so I'm going to write that in meters since everything else is in meters. So this is going to be the wavelength of our laser. Okay, so now all we need is our equations, and of course the important equation, most important equation, is going to be our diffraction relationship. And so we know that m lambda is going to equal d sine theta. D is what I'm solving for. So on your next page, you've got your step 5 where you can work it out, but we're going to put it off to the side here so that we can do this. Now, m in this case, we've got a new symbol here. M is 1. Because we want the first order fringe. The other thing that we've added, though, is we've added one new symbol, and that's going to be theta. So theta is the angle for what's called the path difference. So that means the problem is now telling us, okay, I've got everything I need except I need theta. So I need some sort of expression for theta. And this is, remember, is how you solve all problems. You start off with your most important equation here, and maybe you've got everything you need, and you plug it in and you're done. But oftentimes the problem will say, hey, you need one more thing for us. So we need that theta. So let's go ahead and magnify our drawing like we did before. So here's theta, which is what I want. This is going to be my slit width, and we called this x, but we want this to be equal to 1 wavelength here. Now you're like, but wait a minute, I don't know d, so I can't do that. However, if you look at the diagram here, this angle, theta, is also going to be equal to that angle up there. And we could walk through all of our arguments here so that you can see that, but this angle theta must be the same as that. And if you want to convince yourself of that, let's say that this is a right angle as well. So this angle is going to be 90 minus theta, right? And if this is a right angle, then this must be 90 minus 90 minus theta. In other words, theta. Okay, so walk through the geometry, make sure that you understand. Here's a right angle here, here's my other right angle, and that's how I can figure out that. That's going to be real common. We're going to do that pretty much all the time. So now I know that this is capital D, and I know that my spacing between the two, which remember was measured here, those distances are going to be the same on my big triangle. This is the little triangle. This is my big triangle here. I don't want to draw it in 2 different scales. So now I know that theta must be equal to, the tangent of theta must be equal to my opposite over my adjacent. And so that's going to be A over capital D. I'm going to get rid of these so that we're not too confused with that. There we go. Okay, so hopefully see, I'm going to bring this over to here, and that's A, because those have got to be the same. Here's my big triangle, not my little bitty triangle that I'm drawing here. I just use that to make the association between these two thetas. Okay, so there's my second one. And work through that, but we're going to do that pretty much all the time. So that's worth having in your flip book for this. This is how we're going to get theta most of the time. So theta then is simply going to be the inverse tangent of A over D. All right, so let's do that here. Now we've got everything that we need. We didn't add any new expressions. So I'm going to work out first. I'm going to go ahead and get a number for my theta. Oops, that should be a capital D. And so theta is going to equal the inverse tangent of A over D. And we decided that was 0.16 meters divided by 0.40 meters. And punch that into your calculator, and that will give you an expression. So let's go ahead and take our calculator and let's do it. Let's work out the number. 0.16 divided by 0.4. And I get 0.4. That makes sense. So, and then I'm going to take the inverse tangent of 0.4. Oops, I have to do that first here. And I get that theta is 21.8 degrees. Okay, so now I'm ready to go back to my other expression. M is 1, so I've got lambda is equal to d sine theta. And so lambda over sine theta must equal d. So that's 650 times 10 to the minus 9 meters divided by sine of 21.8 degrees. And so 650 times 10 to the minus 9 divided by sine of 21.8. And I get that the split spacing is 1.75 times 10 to the minus 6 meters. In other words, it's 1.75 microns, which is pretty reasonable. Okay. So make sure you follow that. Make sure, particularly when we're trying to relate how that theta is actually equal to how it corresponds to our big triangle, between the big triangle and the little triangle. And obviously you could say, oh, well, I'll just accept that because Dr. K said so. But it's worth you going through the geometry so that you can see those angles have to be the same. Once I have that angle, then, if this is D and this is A, if you agree that that's going to be that angle right there, then it's pretty easy to see that that then has to be the tangent. Okay, so what you've seen today is that we can use interference to measure very, very tiny differences in distance from that. And that's a hugely valuable technique because in many cases we want to measure something really, really small, but I can't just take a ruler and stick it down there and see what that's going to be. There are lots of applications to this. We can use interference to measure the distance between atoms. We can use it to measure gravity waves that are coming through from space that are causing very tiny changes in space and time from that. All of these things are available because we can use this diffraction pattern from that. So learning how these things interfere with each other and the pattern that they produce is a very important scientific measuring tool that you're going to see quite a bit throughout your career. All right, we'll see you next time.